My name is Don Quimby, and this video is about nuclear decay, developing a formula for it, and explains why the half-life is the same for like 1 milligram of a substance as for 1 ton. I mean, a lot of people think, well, I used to think that if you had 1 milligram, tiny amount, you could poof, it's all decayed. But no, even with a tiny amount like that, 1 milligram, 25,000 years, and then half of that's gone. So you have a half a milligram that's still good and half a milligram that's decayed. Anyway, so let's move along here. I do have a bit of a pre-test here. You can read the thought experiment, and the pre-test, I have the answers. I often give a pre-test. And when I give the pretest, I just give credit for trying. Of course, after that, we teach subject matter and then give a percentage grade for how much of the state standards or whatever they learned. So I'll just scroll down through this rather quickly here, so that, stopping there every once in a while so you can also stop the video and see each of these questions. Wouldn't normally give the answers, but here in this video, kind of need to do it that way, I guess. Oh yeah, and I've written a lot of Bible questions to teach Bible, and then I save that under one file name and then copy over top of it, sort of like a template. Going to the next page. So here we have a box with 128 pennies being represented here. And we're going to shake that box for like 10 seconds. We're using 10 seconds because it's easy. Half-life of 10 seconds. We probably do this in 3 seconds. We're just trying to give all these pennies an equal opportunity to flip. Okay, 10 seconds is surely more than enough. Well, maybe somebody might think, oh, go more than 3 seconds, it'd probably start all going tails. But we can think about that later. Let's move along here. Next page. And that's what I mean. Half of them flipped over to tails. And so those we remove. The ones that are heads, they haven't decayed. The ones that are tails are like the atoms that have decayed into a different atom and have to be removed. And in this case, instead of 25,000 years, it's like 10 seconds that it takes for all of them to have that opportunity. And so we took out the tails, and now we've got these heads left. 64 of them there. And we're going to shake it, and we get tails. 32 of them, if you count, and 32 heads there. So it doesn't matter if the element has trillions of atoms or only 10 atoms. It's going to take, in this case, we're pretending 10 seconds. And here again, all heads, took out the tails. And so shake it again for 10 seconds. Bunch of them turn tails. Go to the next page. We're going to take out those tails, and there's what we have left. 16 heads there, and shake it again. And half of those turn over. Take those out. Down to 8 heads that still have not decayed into another atom. And that's what these pennies are representing, as atoms of an element. And shake it again, and we get these tails. Remove those tails. You have 4 heads left. Shake it again. 2 of those, half. Tails. Remove them. 2 heads. Shake it again. And look at this. I said here at the bottom, we shake the box for 10 seconds. Of course, 10 seconds is more than sufficient, but you still have to use that 10 seconds, even with these two, because you want to stay, consistent with the experiment. And there, one of them turned over. Remove that. Kind of done because we're not going to get half a penny. And here it's talking about, what if we, here's an example, what if we had just 100 of them? 100 is another easy number, maybe easier than 128. So in this example, we use this 100. And so we, after one half-life of, say 10 seconds or whatever it is, 25,000 years, we only have 50 left. Why? We divided by 2. So now here's the 50, this 100 divided by 2. See, I'm kind of outlining, well, now you can imagine that line around there. That's the 50. But we're dividing by another 2. Of course, just by multiplying by 2 in the denominator. And we get 25. So here's the 100 divided by the 25, and we're going to divide by another 2. Each time, it's like here, 2 to the 1. Here it's dividing by 2 2's, dividing by 2 times 2. That's 2 squared. 2 times 2 times 2 is 2 cubed. So we're developing kind of a formula here. Just looking back to see what we did there. Okay, let's scroll down here a bit. And just keep dividing by more 2's. We're down to 2 to the 7, I see there. And even though you have a much smaller amount left, we still have a half-life of 10 seconds. It takes 10 seconds for half of them to decay, even in a tiny amount. It's not like you have this very tiny, 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 tiny number of milligrams or whatever. It's even if you have 0.000381447, don't blow on it, don't blow it away someplace. But even if you did, the atoms would take another 10 seconds or 25,000 years, whatever the half-life is, another half-life period, for half of it to decay. Just like a ton of it would have taken the same amount of time for half of that to decay and get a half a ton. And you could kind of see how that works with the pennies. Each penny was like one of the atoms. And so there we are back to this. Let's go to the next page. Here's another sample problem way of doing this. And I'll let you look at that. Right here we have 17 half-lives. Well, there was a total of 187 seconds or whatever, and the half-life was 11 seconds. And again, this could be years or months or something, days, whatever. I've been talking about seconds. So 187 divided by 11, well, that's 17 half-lives, 17 periods of dividing in half. That brought it down to that. So let's look at another. Here's where we have 173 total grams, for instance. Not going to be pennies here because we're not going to be able to get this fraction of a penny down here. But there were 14 periods of decay, taking the total time and the time for each half-life, 11 seconds. Yeah, I guess I messed up. I said 10 in the earlier one, didn't I? Okay, so I can't go back to that. Here's one where you have 105 seconds for the total time of decay. Or no, for the half-life. I'm getting confused. I guess I better end this video quick. There's another example. Alrighty, and so let's go on. Back. I want to go back. Yeah. So the formula is original amount divided by total time divided by 2 raised to the total time over half-life. And that equals the amount remaining after a time of the total time here, 416 in this case. Okay, so go on to the next page. And there's the credits, which are just a joke. And you can like this if you want to. Subscribe for some reason. I don't know what that's all about.